All right, today we are diving into something called diffraction. Now, it might sound a little technical, but it's a phenomenon that's happening all around us all the time. We're going to see how this simple idea, a wave bending, is the key that lets us unlock some of the deepest, most incredible secrets of the universe. I mean, think about this for a second. How on earth can we know what a star is made of when it's hundreds of light years away? We can't exactly go out there and scoop up a sample, right? It sounds impossible. But the answer is hiding in the light that travels all that way to reach our telescopes. And the tool we use to decode that light? Well, that all comes down to diffraction.
So, here's the game plan. First, we'll talk about what it even means for a wave to bend. Then we'll get into the why with something called the ripple effect principle. After that, we'll meet our hero tool, a kind of super sieve for light. Then, the fun part, decoding light's secret barcode. And finally, we'll put it all into practice. Let's get started.
Okay, section 1. Let's get right to the heart of it. What exactly is diffraction?
So here's the textbook definition. The key words here are spreading and narrow gap. The best way to picture this is to think of waves in water. Imagine a wave hitting a wall with a small opening. It doesn't just punch straight through in a neat little line. No, it fans out, it spreads, it curves into the space behind that wall. That spreading effect, that is diffraction, in a nutshell.
And this slide, this is crucial because it shows you the golden rule of diffraction. See on the left? When the gap is really wide compared to the wave pretty much just sails on through. A little bit of bending at the edges, but no big deal. But now, look at the right. When that gap gets narrow, when it's about the same size as the wavelength of the wave itself, bam, the effect is huge. The wave just fans out everywhere. So that's the big takeaway. You get the most dramatic diffraction when the gap is tiny.
Okay, so we know that waves spread out. But why? Why do they do that? Well, the answer comes from a really brilliant insight from way, way back in the 17th century. This is something called Huygens' principle, and the idea is actually kind of simple but really powerful. It says that you should imagine every single point on the edge of a wave as its own little tiny source, sending out its own little circular ripples, which we call wavelets. The next big wave is just formed by all these little wavelets overlapping and adding up. It's like a constant chain reaction of new waves being born from the old one. You know, I absolutely love this analogy from the YouTube channel E10 Physics. It just makes so much sense. Think of the main wave as the teacher. It passes on its knowledge to a line of students. That's the new wave front. Now, every single one of those students becomes a new teacher, spreading that knowledge even further out. That's exactly what's happening. And that's why, when a wave hits a tiny gap, the few points that sneak through act like new teachers, spreading the wave out in every direction on the other side. So we know light can bend. That's cool. But how do we actually use that? Well, let me introduce you to the real star of our show, the diffraction grating. So what is this thing? Just imagine a piece of glass or plastic with thousands, and I mean thousands, of tiny parallel slits carved into it. They're incredibly close together. So when light hits this grating, it tries to pass through all of those slits at once. It diffracts through every single one, creating thousands of new little waves that all start spreading out and overlapping with each other. And when all those waves start overlapping, something amazing happens. In most places, they're all out of sync and they just cancel each other out. But, and this is the magic part, in a few very specific directions, all those thousands of little waves line up perfectly. They add together, they reinforce each other, and they create these incredibly sharp, bright spots of light on a screen. We call these spots maxima.
And it all boils down to this one beautiful little formula. This is our golden rule for decoding light. D is just how far apart the slits are. Theta is the angle to one of those bright spots. N tells you which spot it is, the first, the second, and so on. And lambda, well, that's the wavelength of the light itself. This equation is the bridge between the tool we build and the light we're trying to understand.
All right, so now we have our tool and our formula. Let's connect this all the way back to our original question. How do we figure out what stars are made of?
This is the aha moment right here. What if, instead of one color, we shine white light, which is a mix of all the colors, through our grating? Well, look at our formula again. The angle, theta, depends directly on the wavelength, lambda. And different colors of light have different wavelengths, right? Blue light has a short wavelength. Red light has a long one. So what happens? They each get bent by a different amount. The grating splits the white light into a stunning rainbow, a full spectrum of color. It's like a superpowered prism.
And here is the final brilliant piece of the puzzle. It turns out that when you heat up an element, like the hydrogen or helium inside a star, it doesn't just glow white. It emits light only at very specific, very precise wavelengths. It creates a unique pattern of colored lines, basically a fingerprint or a barcode of light that is unique to that element. So we can take the light from a distant star, pass it through a diffraction grating, measure the angles of the bright lines we see, and use our formula to find their exact wavelengths. Then we just match that barcode to the ones we've measured in labs here on Earth, and we can say with absolute certainty, yup, that star has hydrogen and helium in it, all from light years away. It's incredible.
Okay, the theory is awesome, but let's get our hands dirty and see how this actually works by running through a couple of real problems.
So here's a typical example. We're told how many lines the grating has per meter, which lets us calculate d, the spacing between each line. We're given the angle to a bright spot. We just pop those numbers into our golden rule, solve for the wavelength, and in this case, we find out the light has a wavelength of 460 nanometers. That's a nice, distinct shade of blue light. Simple as that.
Let's try one more. Here, we have a different grating, and we're looking at the third bright fringe out from the center, which we see at a steep 78-degree angle. The process is exactly the same. First, find the slit spacing from the lines per meter, then plug everything you know into the formula and solve for that one missing piece, the wavelength.
And when you run the numbers, you get 652 nanometers. So just by measuring an angle, we've identified a very specific wavelength of red light. This isn't just a textbook problem. This is literally how astronomers do their work every single day.
Okay, so let's zoom back out from the math for a second and think about the big picture. Here's a classic exam question. How would you explain, in your own words, how a diffraction grating actually produces that pattern of bright spots? And here's the perfect breakdown, a summary of our whole journey. It starts with light diffracting, or spreading out, as it passes through all those thousands of tiny slits. Then, all those new waves interfere with each other. Where they interfere constructively, they build up to create sharp, bright spots. And crucially, the exact location of those spots depends on the light's wavelength, all thanks to our golden rule equation. That's the whole story. And that really is the heart of it all. It starts with something so fundamental, a wave bending around a corner. But when we harness that simple principle with a clever device like a diffraction grating, we create a tool that is so powerful, it lets us analyze the chemical makeup of stars across the galaxy. It's just a beautiful example of how basic physics can lead to mind-blown discoveries.
So it really makes you wonder, doesn't it? Learning how to bend light in just the right way revealed a whole hidden layer of information, the spectrum of colors. What else is out there, hiding in plain sight? Just waiting for us to find a new way to look, a new way to see the world. Something to think about. Thanks for tuning in.